that case.
Do I need to turn it on?
Should be on, yeah.
Okay. It doesn't, I don't hear it. Okay.
You won't hear it.
All right. Sound.
And this should be working. Yes.
Howdy. How you doing? Yeah, I want to see good for you. Oh, business? Come on, come on. What? No one is. Maybe it'll show up.
That's fine. So you can just sit there.
Okay, so it's a pleasure to introduce Dr. Yashar Hezaveh today, who's flown in for the day from Stanford, where he is a Hubble Fellow working in Cavities Institute there. So we'll work back in time. So he's currently a Hubble Fellow at Stanford. Before that, he got his PhD at McGill University in 2013. And prior to that, got his undergraduate degree at the University of Victoria, where he worked with Julio Navarro in 2008. So Yashar worked particularly on strong lensing and high redshift dusty galaxies, and he's going to tell us today about the nature of dark matter on small scales. So.
All right. Thank you. Thank you very much. Thank you for the invitation. It's really a great pleasure to be here to talk to you about these lenses. So these are a few of our gravitational lenses that we discovered with the SPT. So what you see here are the HST images in blue and ALMA continuum images of the lensed background galaxy in red. And so today I'll be mainly talking about how we can use these systems, strong lensing systems, to learn about dark matter and the small scale distribution of dark matter in the lensing galaxies. So that's where we're going with this. And so I just kind of step back a little bit and give a little bit of an overview and science motivation for this. So the past few decades, we've measured the large-scale structure of the universe very accurately with high precision, with many different probes like the CMB, BAO, galaxy correlation, weak lensing. And so we know that these large-scale structure matches the predictions of our simplest model of dark matter, cold dark matter, very well, very accurately. So on these scales, things seem to be sorted out. But when we look at smaller scales, if we look at one of these halos of a galaxy, we realize that there's a lot of structure to them in n-body simulations from our theoretical perspective. And observationally, there seems to be very little information that we have about how dark matter is actually distributed on smaller scales. And one reason why this has become a relatively hot topic in the past decade or so is that in the Milky Way, our predictions for the number of subhalos seems to disagree dramatically with what we actually see. So n-body simulations of cold dark matter predict that the halo of the Milky Way should be composed of tens of thousands of dwarf satellites, so subhalos. So these are basically just clumps of dark matter in dark matter-only simulations. And so the natural implication of that for a while now has been that each one of these subhalos would accrete some matter and form its own little mini galaxy. And so if we look at the Milky Way around us, we should see perhaps tens of thousands of these dwarf satellite galaxies, dwarf satellites. And now, after more than 2 decades or more of deep searches for these things, we found maybe tens of these, maybe something around like 30, 40 now. So this is a plot from Luis Rigard's paper this is almost 10 years ago now, showing this, which has been called now the missing satellite problem, showing the discrepancy between the number of dwarf subhalos in n-body simulations compared to the satellites of the Milky Way. So this is a little bit outdated now. So the number, is probably somewhere around here, if I'm not mistaken. Now, in the past few years, we've discovered more satellites, especially with DES recently. But there still seems to be some discrepancy here. and the discrepancy seems to be growing more as we go to lower masses. So generally, two solutions have been proposed for this to resolve the problem. And so the first one has to do with baryonic physics, and which just says that actually the subhalos could probably, possibly still be there, and we have all these subhalos because of CDM formation, except that they don't have baryons. The star formation efficiency is low in lower mass subhalos, so if they don't have any baryons or gas or stars to show themselves, we cannot expect to detect them directly using direct observations. A slightly different version of that, today I talked with Andrew Wetza, Andrew Benson, and you, and so everybody kind of, there's another level to that also says that baryons could also affect the underlying structure of the dark matter itself too. So that's another factor to consider here. The second solution seems to be modifying the whole dark matter properties altogether. So the idea here is that if dark matter is not really purely cold and has some finite thermal temperature, these random motions basically are equivalent to having a free streaming length. And structures below the free streaming length will be washed out, so it will be smooth below that free streaming length. But on larger scale, it will still look the same. So a warm dark matter model that predicts something like that will still have the same agreement on large scale structure that we have. But on smaller scale, will be power will be suppressed, and so we'll see some smooth structure for the dark matter halos. So our goal here is trying to basically map the distribution or measure the distribution of dark matter on small scales in halos of galaxies to try to relate it to the physics of dark matter fundamentally. And the most important thing here is to try to use a purely gravitational probe that we can actually attribute whatever that we see to the gravitational field and the density field rather than some bias due to baryons. And so fortunately, we have a tool for that, and so our tool is strong gravitational lensing. And imagine there's a background source, there's a galaxy sitting at high redshift, perhaps redshift 3 or 5 or 6. There's a foreground lens, and so the light rays of the background lens background source, as they pass near the foreground lens, they get deflected, they get bent because of gravity, and they come to us. And so as a result of that, from our perspective on Earth, we see these multiple images rings of the background galaxy around our foreground lens that's in blue here in this image. This is another little simulation showing this background source, the red source going back and forth behind the foreground lens. And so you see these multiple images. So in reality, we'll just see a snapshot of that. We don't see these motions because those will take on many millions of years timescales. But we see these multiple images in one case, and the idea is a little bit like looking at images of fish in a fish tank. If you look at a fish tank from the corner, you see two images of the same fish, and that's because the light is getting bent because of refraction coming to you from the two different angles. So here's the same idea that you have these multiple images of the background source. So again, so idea is that now we use these multiple images to try to probe to see if this lensing galaxy in the center is clumpy or smooth by the gravitational influence of its matter on the images. The reason we need strong lenses to do this is actually that they generate multiple images of the same background source, and that is a very important idea here. So we generally want to have multiple copies of the same background source so that we can distinguish the effects of intrinsic source morphologies from the distortion done by subhalo. So in this case, for example, you can see that if there's a subhalo sitting right there, then it distorts the image of that one image, but it leaves the other images relatively undistorted. So when we do the modeling, in fact, it's the comparison of the different images, so this image to the other images, that gives away this extra distortion by subhalo affecting only one of the images. And also to give you a sense of scale, this is the dark matter of a Milky Way kind of sized galaxy, the dark matter halo. And so these would be kind of the strong lensing arcs that you would see from a galaxy-galaxy lensing system. So they're very small compared to the size of the halo that you're trying to look at. And so even though the halo itself might have tens of thousands of subhalos, our expected detection rate is actually very small because we're really probing just a pencil beam through this halo. And that is one reason that I'll come back to later, that we need a large number of systems so that we can actually build up our statistics to learn it's statistically something significant. Also, to give you another sense of scale here, this is showing the effect of a dark matter subhalo, a 10 to the 9 solar mass subhalo on the images. And actually, this is a very massive subhalo that is located somewhere around here. And I don't know if you notice, you'll see the images are actually changing as the subhalo is popping in and out. And just to guide your eyes, I'll just show this. It's just like coming in and out, and you can see the distortion a little bit in the image here. It's a very, very subtle distortion. And actually, in this case, this is a relatively massive subhalo. So as we go to lower masses, the effect is actually even more subtle and difficult to detect. So when we're doing our analysis, we need to be very careful about finding these tiny image distortions that are indicative of the presence of subhalos in the images. And so kind of that brings me to the next topic, which is like how we actually measure these distortions from the images that we have, from the data that we have. So typically in any strong lensing system, we measure any parameter that we're interested in by simulating observations of the whole data that we have, making simulated observations. And so our simulated data is a function of a few parameters. And so if those parameters are what we're interested in, we can map out the likelihood of those parameters as we vary them and compare it to the data. So for lens modeling, typically we have parameters that describe the light distribution in the background source, just how that background source looks like without being lensed. We also have parameters that describe how the foreground lens, mass in the foreground lens is distributed. For example, this could be some NFW or a combination of these, or you might have subhalos or without subhalos in it. So basically just describes what the projected density looks like. So using these two ingredients, we can now predict what the sky model should look like, perhaps an arc like that. Then we have some new parameters like PSF issues or pixelation, and we can add those to that. And then basically we should have a noiseless perfect version of our data. And so using a maximum likelihood method, we can map out our probability of our model parameters here given the data. So that last bit of comparison, it gets a little bit tricky when we're looking at interferometric data like ALMA data, because they don't actually just measure the sky brightness, but the 2D Fourier transform of the sky. So interferometers basically, between every pair of antennas, they measure one Fourier mode of the sky emission. So if the sky looks like that, for example, if we have a strong lens system that looks like that, we have an arc here and another counter image on the other side. And we have one pair of antennas, the two pair of antennas, one pair of antennas basically measures just one Fourier mode. And we can plot it in our Fourier space plot. So this is basically kx, ky of the Fourier space, which in interferometry is labeled usually u and v. And so there's one mode, so we can just put one dot there. That's the mode that we have measured. And if you take the inverse Fourier transform of that to look what the sky emission looks like, we just have a sinusoidal mode. Because of the one mode, it's not very exciting. But as we add more antennas and more measurements of different modes and add them together, we start recovering the true signal that it is sky emission that we have out of there. So generally, the more antennas that we have, the more complete our Fourier space sampling is, and the better our image will look like. But generally, when you look at an interferometric image like that, these fluctuations that you see there are not necessarily noise. They're just part of signal because of the incomplete sampling of this space here. So for the same reason, you can imagine that if one of these antennas here, one of these measurements happen to be very noisy, that noise starts leaking everywhere else. So the noise is very correlated in that space too. So when it comes to interferometric data, we actually try to analyze our data in this space, which is where the noise is Gaussian and simple, rather than getting into messy deconvolution issues in the other space and correlated noise issues. So in our lensing approach, once we have a simulated model for the sky emission, then we can take the Fourier transform of that, sample it at the position of the antennas, the the UV coordinates where ALMA has measured, and perhaps add some additional parameters for nuisance parameters like antenna phase errors and things like that that we later marginalize over them, and then form our likelihood in this space. So now I just want to remind you that we have parameters for the background source and the foreground lens. Using these two, we can have a prediction for what the sky emission looks like. So this background source, actually, we can parameterize it in different ways. It's up to us what the choice of our parameterization is. In the past, a few years ago, I used to actually parameterize it by using a bunch of Gaussian blobs. So we would just, depending on our resolution, put like one Gaussian blob, and then maybe like, if it didn't fit well, we would do two Gaussian blobs, or move on, something like that. But ideally, we would like to have a parameter space that is very flexible, that can allow for very complex morphologies for the background source. You can imagine there could be a background source that, I don't know, it might have a ring to it, or some, merger structure that could be very complex and not easy to capture by a simple set of functions like that. So we can actually do this by pixelating the whole background source. So we allow our model parameters to basically be pixel values of a pixelated source that has a lot of freedom to fit for any shape that we want here. And once we formulate it that way, actually we can do our lensing using a matrix multiplication, where our background source is basically treated as a vector. So you can imagine that I can arrange all these pixel values into one long vector here. And there's a lensing matrix L that when I multiply it by that vector, it gives me a vector of the sky emission, what it looks like. So the set of parameters that describe the lensing galaxy, the distribution of matter in the lensing galaxy, they go into this L matrix, that is the lensing matrix. So for a mass distribution, I basically define how my image transformation, the lensing transformation goes, and the rest of my parameters are basically, they go in the source vector here. So we're splitting the parameters into basically these parameters that are nonlinear, and so for them we need to solve to get L, and also a bunch of linear parameters that are source. So what's interesting here is that our sky surface brightness is linear into, with these source parameters here. But as I mentioned, we also want to have the Fourier transform of that. So we can add this F matrix on the left side of that, which is basically a matrix that gives us the Fourier transform of the sky emission. So this F matrix, basically every row of it gets that image on the right and predicts one mode for that by just multiplying by these e to the minus IKRs. Yes?
So in general, how many pixels do you have in the observed plane and the background plane? Because your mapping is obviously going to be funny in terms of the area of one pixel and mapping to the area of another. Sort of curious what kind of optimal number of pixels you settled on.
And so here on the left side, we don't have pixels. We have the visibilities, as you see. So this fine thing maps it. We need to have a resolution here that is at least higher than our Nyquist frequency that we get from the longest baselines that we have. On the source, it's kind of tricky because the lensing magnification is variable. So you have areas where you have. So one thing that I actually skip about mentioning is that we do have a prior on that background source, because an issue with this is that we could actually overfit by having too many pixels. So there is a basically a smoothness prior that we do. Now I can imagine that in the limit of low signal to noise data, that prior becomes very important and we need to be careful. But we've done it simulation, and so these are like such, with ALMA data, it's so high signal to noise that the data is really driven by the fit part of it, the likelihood part. Right?
I guess I'm sort of, at the end of it, also just curious how big these matrices get. So.
Huge. So yeah, absolutely enormous. So I'll get to that. So these sources, they're for this data that I'm talking about, they're 200 by 200, something like that.
Okay.
So that's 40K, right?
Yeah.
And then we actually have two channels. So that's 40K times 280K. V here could be a few millions even after. So I'll come to that. Actually, computation is a very difficult problem to do. Yeah.
I wonder how strongly the lensing matrix and the source vector
there's some degeneracy, and so we'll marginalize over these uncertainties that we have, either in between the lensing and the source, or even there are some parameters that go into F, like the antenna phase errors. So we marginalize over those uncertainties, but there's some. There's nothing that is like super degenerate that are like, but within a Gaussian approximation, like a Fisher approximation of those degeneracies, we marginalize over them.
Okay. Can I ask a follow-up on the question? Do you want to do your question?
I can add a little. So I wonder, because I can naively think any structure you see in the lens could be just some representation of this fine structure in the source.
No, because you have multiple images.
Multiple.
Yeah, that's exactly the thing that I mentioned at the beginning. That remember, you have 4 images of the same background source. So if I see some funny shape in it and I try to modify my background source to fit that, it's going to start to disagree with the other image, and the other image, and the other image. Right? So that's where you can distinguish. That's where that degeneracy that you were talking about breaks. So if you had a single image, there is a perfect degeneracy, and there's nothing we can do about it. But that degeneracy, breaks, when we have multiple copies of the same background source, basically.
So the possible phase space is sort of contiguous?
That's very complicated.
As in you're not going to have two completely different, like a completely different source and a completely different lens, and then over here a completely different source and a completely different lens fitting the data. It will probably be a case where all of the solutions kind of cluster together. Is that kind of
right. So I think the main prior that you have on this is that these images, they all come from, it's the same one background source, right? So there's some. So actually, you're right. So there is one solution to every strong lensing problem, which is there is a background source that just looks like that, and there's nothing in the middle, right? That is, and believe it or not, we used to talk about that with my advisor during my PhD a lot, and now I run into this all the time. Actually, my code comes up with that immediately. That's the easiest solution to find, because it just immediately finds that you can just suppress mass to low, or even if something I put a prior, I just like try to kick it, to the higher masses. It just slowly gets the galaxy out of the way, pushes it out, and it tells me that's the image. I'm like, that's junk, right? But once you have that prior, that these are actually the same images of the background. So once you go to that parameter space, then it becomes very hard to fit them without going at the right, because then they have to match each other in the source plane.
So as a part of that, when you've got this L matrix here, when you do a singular value decomposition on it, how many eigenvectors do you find actually matter? 3, 4, 10, 100?
I've never looked at the, what an SVD would give me for that. But I think you'll see. So I think if I go to 2, 3 slides up, so this is what. So once you have this, F and B and L matrices that we have, to find the source structure, you need to solve for this thing. Actually, it's a little bit more complicated. So now we have this is the source prior, and these are the matrices that we talked about. So that B is also a primary B matrix. So it's not clear to me which matrix we should think about the eigenvalues of and what exactly they would mean. But we can talk about it after. Yeah. Okay. So as I mentioned, so the idea again here is that we can split these parameters into the source parameters linear, lens parameters nonlinear. So now we can actually non-linearly only sample our non-linear lens parameters that are fewer. And at every step of that, marginalize over these linear source parameters that are enormous. So there's like tens of thousands of them. So Warren Morningstar is a grad student at Stanford working with me now. So last year he was doing a lot of tests where he would generate mocks and then lens them, get ALMA data sets, put it in a pipeline, and try to test it, make sure that he can recover the background source and also sample the posterior of the lens model parameters, and that there's no significant bias in anything. This is another example. So this is a mock data. So you see this gravitational lens. There's like a merging image here, another image there. And so once we actually apply this, we can reconstruct the image of the background source. That's what we get. Notice there is like some noise. I don't know if you can see it, like dark blue here. And this is what the true source was. So this is a mock data again. So this is what the true source was without noise. Yeah, as I mentioned, so this is computationally very difficult. So actually the size of the matrices, just the size of that, basically this combination of these three matrices is something around like 3-4 terabytes. So we need to actually put it on distributed systems, and every likelihood evaluation on like 4,000 cores takes something about like a couple of minutes. And we need to do many model evaluations. So we need thousands of model evaluations. So computationally, it's a very difficult thing. Not for every data set, but for like the data set that I'm going to talk about briefly, that's what we had to deal with, especially at highest resolution that we're talking. So one thing to speed up this otherwise difficult calculation when it comes to subhalo searches is actually linearize the whole model. So remember, just here we have these linear parameters, if I go back, and linear parameters and nonlinear parameters. But once we get a smooth model, a good model for our halo that doesn't, for our main galaxy that doesn't have any subhalos, and now we want to look at the perturbative effect of a tiny subhalo. Now we're in a regime with such tiny perturbation that we can linearize even the effect of the nonlinear parameters like the mass of the galaxy or its ellipticity and things like that. So we can take the derivative of our observables and basically make a linear model, and now that speeds up our calculation quite a lot because we can find the best fitting model or marginals over our posterior for a particular model that has a subhalo in it much faster without needing to non-linearly go and sample tens of parameters. These are the effects showing what the linear search looks like for a subhalo model. So basically what we're looking at here is these are two mocks. So on the left side, there's a mock. There you see the lensed arcs. And in the mock, there are no subhalos. So there's a galaxy sitting at the center, no subhalos, the lensed images that look like these white arcs that we have here. And the grayscale is showing the difference in marginalized log posterior between a model that has a subhalo in it and a model that doesn't have a subhalo in it at that particular position. So we have a model that is the smooth model. That's our, that's a null hypothesis. And then at every location, we put a subhalo. We basically do a grid search for the subhalo parameters. So again, we split some of our parameters out. So the subhalo parameters are its mass, position, x, y. So we search all that space by placing a subhalo of a certain mass at that location, get the marginalized posterior, and ask ourselves how much better or worse is it compared to the model that doesn't have a subhalo.
Do you also modify the source when you're doing this?
Yeah, so for every one of these models, that's what I mean by marginalized. Okay. So that's marginalized over the source parameters, antenna parameters, and even the lens parameters within the linear approximation that we have around that. Yeah, thank you for the question. So in this case, you can see there is no subhalo, and every black here is basically ruling out the presence of a subhalo by something like square root of whatever that is. So over this area, we're looking at least 5 sigma exclusion of a subhalo in that area. The right panel, there's a subhalo in the mock at that blue circle position, and the red is showing you that you actually get an improvement about like 4 or 5 sigma at the position of the subhalo. So we can actually detect the subhalo at that location. So there are two important parts to that. One is that we can actually detect them when they're there, and the other one is that we can exclude them over certain areas by some probability if they're not present at a certain mass.
What's the contrast ratio between the mass column in the subhalo versus the rest of the data set? And presumably you have some contrast over which you can detect them, and then if they're just too weak, you don't see it, right? So
yeah. So as we go to lower masses, then our sensitivity drops. That's true. So we've never looked at it or thought about the contrast. So typically, and that's a caveat about all of this, is that we have a fixed density profile for our subhalo, right? So we have a pseudo Jaffe, which looks like an isothermal with a cutoff for the subhalo, and so we basically, I mean, you can imagine because it's singular. I don't know exactly how to define that contrast, but yeah. But so these are here and done at, I think, 4 times 10 to the 6 solar masses for the subhalo. And the lensing galaxy itself is a few times 10 to the 11 solar masses within this area. So that's the lensing mass.
So for the subhalo itself, then, does that mean that there's just a single parameter, which is the mass, and beyond position, I guess?
So mass and x and y.
Normalizing.
Yes,
Sorry?
mass, x, and y. Yeah. So there's just 3 parameters for it. Yeah. So now we're thinking about like perhaps it's. So I talked to James Bullock, and we were talking about how actually we can translate this to simulations, and now I'm starting to think maybe it is worth allowing for more freedom in the profile of the subhalo. Although I'm worried that it could be too degenerate, and if that is, then we'll learn something there too.
You should at least know, coming back to them, like what spatial scale the mass is actually coming into the distortion, which
Yeah.
you could turn it into just a constrained mass within a given physical aperture.
That's right. Yeah. Yeah.
Which would be robust, I suspect.
Yeah. So do you think that if you were to fit an NFW and allowed the concentration and the mass or RS, these like to be kind of free parameters, would that answer that question?
Well, I don't think you'd have the resolution to really constrain the additional parameter with concentration, right? I would think that the robust answer is some aperture in which you cut a mass.
Okay.
I mean, that strikes me as the most robust quantity you could, but I don't know when it comes to actually forward modeling it through your pipeline, how much, because you are at some level sensitive to the extended profile in the cross correlation of the modes. I guess the question is how much information is there versus within some smaller spatial scale where most of the signal is
Right.
coming.
Mm-hmm.
Just seem like a subtle.
Mm-hmm.
Yeah.
Okay. So now I jump to talking about data. So this is SCP-81. So what are you looking at is a strong lens. Blue is the HST image of the lens. So that's a stellar, stellar light that goes, way beyond this. Red is the ALMA image of the background source. Basically, the dust continuum in band 6 in this case, I think. And so this is an extremely exciting data set. So this was taken as a part of the science verification for ALMA at long baselines. So the first time that ALMA was looking at sources at 16-kilometer baselines. So that's equivalent of something about 20, 25 milliarc-second resolution. And so the data was released, was made public in February last year. So as soon as they did that, we started working on this to try to see if we can learn anything, apply our pipeline to this data set and learn something from it.
What's the scale of the lens here?
You mean here? So this is about 3 arcseconds-ish, the diameter, or maybe a little bit more, yeah.
Like physical scale? Like
So
the lens?
So the lens is at redshift 0.3, so we're looking at probably 10, 15 kiloparsec radius, 10 maybe. Those are very rough numbers, probably. So yeah, I really like it how people mention that it looks like you can see the HST pixels here in comparison to the structure in the source. So this is our reconstruction of the background source. So you see band 6 and band 7. So the data it has been taken in different bands, band 4 and 6 and 7. And so these are different frequencies. So that's what the SMG at redshift 3 looks like down to about 100 parsec resolution. And so once we have this reconstruction, and now we run the subhalo finder over this. So we started with band 6 analysis, and so we get this positive that was, I think it's about 4 sigma, if I remember correctly, 4.5 sigma. Was kind of interesting, but I was worried that it could be a lot of other things that we didn't account for, some systematic. We looked at band 7 data that was taken at a different time. We see like a consistent pattern between the two, and the peak is happens at the same place. And so we did a joint analysis. Basically, now we have 2 different planes for the background source at band 6 and band 7, separating them. And so in the joint fit, we had this thing that we thought was basically a positive detection. So remember that we were doing this search using the fully linearized model. So now we find basically a peak in that parameter space that corresponds to these subhalo parameters. So we actually go back to our nonlinear search and allow it to sample that, place in the parameter space nonlinearity. So these are all the parameters that describe the mass distribution in the foreground lens, including the last three are the parameters of the subhalo. And so that's I think the one, so this one here is the mass that is 10 to the 9 plus minus 1 dex. That's the mass that we derive for these. Again, like assuming that, with the assumption, with the caveat of assuming that density profile for the subhalo. Okay, so once we account for this and we assume that this is the dark matter subhalo that we've detected, we add it to our macro model, to our main model, and we search for an additional subhalo. Can we find another one? And we go back to the model and we don't find anything. So everything looks like an exclusion now. So combining, so these basically, they go searches for subhalos from 2 times 10 to the 7 here to 10 to the 9 solar mass. And you can see that our sensitivity basically goes down. So the lower contrast, you see basically our sensitivity is lower at that region. And you can also see that our sensitivity is it's spatially different. So the area over which we're sensitive also depends on the mass. We can do some statistics, jujitsu, combining these like exclusions with that detection to get some constraints on the mass function of dark matter subhalo. So it's a little bit complicated combining these Poisson statistics of the subhalos popping out with the Gaussian statistics that we have between the two models, competing models. But these are the error bars that we get. So this is the mass function going from 10 to the 7 to 10 to the 9 solar masses. This is the projected density, projected numbers. So this is d and d log m. For the bin where so these are 95% error bars. So for the bin that we have a detection, we can also have a lower bound. For the other ones, we can only place an upper bound. Now for comparison, this gray area is from Dalal and Kochanik 2002. So for those who know about that, that's the previous lensing measurement. So if we scale those, basically their 95% limit to what we think, for this particular galaxy, that's what should be expected from that measurement. And I think that's consistent with CDM generally.
What's the slope of that?
Well, the slope in those things in n-body simulation is 0.9. So the next plot may say that. So this is basically now if we can actually fit a power law to these things. So that's what we do. And so these are the parameters for the power law. That's the slope, and that's the normalization. So n-body simulations, they're somewhere around there, with very little scatter actually. So what's on top is actually, just basically slicing through this. It's not marginalized on top. It's just a slice of that. It's a trace of that. And the histograms are actually showing what's predicted from n-body simulations. So these are plots from Yao, who is a grad student at Stanford. Now, the range is supposed to imply that there's actually a lot of uncertainty in the predictions themselves. So what Yao is changing is the ratio of the concentration of the subhalos. This is the concentration of their distribution, not their profile, to the concentration of the main halo. And each one of them itself has this large spread because of the intrinsic scatter in the simulations.
Can you just go back to the previous plot?
Yeah.
Like, if you just wanted to go down one subhalo mass to the next one, what data would you need? Like just, you have a detection at 10 to the 9.
Right.
We wanted to do your best to get a detection of the next one. What data would you need? Would it just be more?
Yeah. I'll mention that in 30 seconds probably. Yeah. So this is just like working on Yao's plot. So this is just like the same error bars in all the 4 panels, and just showing how the predictions from simulations, they vary as we look at the different properties of the host halo. So for example, the concentration of the host halo, we change it, we get different predictions. So this is something I was talking to Andrew today about is that we can actually, it seems that in the future we actually need to put a lot of effort into narrowing down our uncertainties, theoretical uncertainties on our predictions when it comes to comparison to the measurements. So now to your question. So actually, yes, I showed this and I was very excited about it a few weeks ago, and somebody said, they look like crap, there's like, all this, there's just error bars and whatever. The thing is that over the lensing area, we expect about 1 detection in this area altogether. So that's just because of this area that, if you remember one of the first slides, there's a tiny pencil beam that we were probing. So statistically, we don't expect more than one detection in this area altogether. So the way to actually have statistically significant measurements here is actually increase the number of sources and look at different sources. So that's the plot that I want. So in this area, right now it looks, so there's a very good probability that actually there is nothing in that area that we can probe in this region. And but with more sources, there is a probability that one of these subhalos will sit somewhere here, here, there. And combining those, we should be able to measure a global mass function.
Is it surprising that the very first one you looked at had the largest subhalo, or did you expect this to not see anything?
It is surprising. But I mean, hopefully they're there.
What was the mass of the host halo in the example you already showed and derived?
So I don't remember the number.
You found something that's 10 to the 9, but was that halo 10 to 12?
Yeah.
So.
I mean, these are massive. This one is a massive galaxy, so yeah. Not all the strong lensing systems are as massive, but this one is a massive galaxy. It's not complete.
If you plot the 1 dark matter to KV, where the prediction?
Well, I've been told that the turnaround is somewhere around here, no? Like,
That's a worm. Okay.
Isn't that around 10 to the 8?
That's an worm. Over 2 kV.
For the, for the 2 kV. Well, there was another recent paper, Lee et al., and so I think they were kind of showing that a lot of these different dark matter, warm dark matter models, the cutoff happens around a few times 10 to the 7, so somewhere around here maybe. But the 2 kV, I think it's about here, more or less. I mean, it's not a sharp program, but So that's one thing. So I'll briefly talk about that. So the thing is, if you remember at the beginning, so we need more sources to measure this part with higher precision. And so fortunately, there are a lot of strong lenses now. So that was a part of my, mainly the focus of my PhD was actually discovering these strong lenses in surveys. So I was a part of the SPT. And so now with SPT, Herschel, ACT, Planck, so there's actually, if I'm not mistaken, a sample of a few hundred lenses that we can target with ALMA to look at them for substructure. So on that front, things are good. So we have some data from cycle 2. This is another SPT lens for cycle 2 for substructure analysis that I'm talking about. So again, in blue we see the HST image. In red you see the ALMA. And so the ALMA image here is about 40 minutes, and what you're seeing here is the signal to noise. So basically at the peak you're looking at 140 sigma. So they're extremely bright. We're really in a regime of very, very high signal to noise here. So when we go to lower masses below our threshold, having a lot of lenses doesn't really help us, because as you can see, our error bar starts to kind of blow up here. So having 20 lenses doesn't do anything. So I'm briefly, in the remaining time, going to talk about 2 different approaches that we hope we can use to extend our sensitivity to lower masses. So the first of these methods has to do, I always think ironically, has to do with the size of the background source. Actually, what is limiting our sensitivity here at 10 to the 7 is not because ALMA is not high resolution or sensitivity, it's because of the size of the background source. So here in the 3 panels at the bottom, there is one subhalo that is sitting, it's the same subhalo sitting in the middle of all the 3 panels. What I'm changing here is the size of the background source. And you can see as this source becomes bigger, it becomes even, visually it becomes more difficult to see the effect of a subhalo lensing. So if it's very small, you see this distortion, that hole that is punched through this by the subhalo, and as we go larger, it starts kind of washing away the signal. So you can imagine that if the size of the background source is much larger than the distortion that we're trying to look at, it becomes very difficult to see it because the signal has been washed away. It's a little bit like putting a lens in front of a white wall. It doesn't do any distortions because there are no features. So this is another example. So you can see on the left side, there is a subhalo sitting there, but there's a blue big background source, so it's very hard to see the effect of lensing. But now, if we could paint the background source with different colors, like the case on the right, you can see that here there's a lensing effect, a subhalo lensing effect taking place. So even if you have larger sources, if somehow we can break them into smaller pieces, that could increase our sensitivity. And so the idea here has been to use velocity information. So the velocity structure of the background source. If we look at them in molecular lines, in each velocity channel that we're looking at the smaller part of the background source. And so with a kind of a joint analysis of these different velocity channels all together, we should gain some information that basically breaks the degeneracy of the surface brightness with the foreground lensing parameter. So in effect, we will be doing like a 3D lens modeling with the third dimension, with the velocity dimension, the full model of the data cubes. So this was a work from a few years ago. So we did Fisher analysis for combining these data first basically integrating over them and then modeling them. That's the gray areas, the gray contours that you see, versus having the 3D information. That's the blue ones that you can see. So this is the mass of the subhalo. So you can see we actually gained a lot of information from that. So we're just in the process of doing that. So this is one of the molecular lines from cycle 2 data that we have. So this is a CO line. Same source that I showed you before. So every channel that you're looking at is a narrow channel. And you can see the morphology of the background source actually varies as you go through these channels because in each of them, we were looking at a smaller part of that. So that's one way. So we're hoping that by doing this, basically, we can increase our sensitivity to lower mass subhalos by some amount. Then maybe we can go a little bit more down. We'll see. That depends. That also depends on the morphology and kinematics of the background. So you can imagine if the background sources were had high velocity dispersion all over them and very, very diffuse, then you're not gaining much information out of that because in every channel they will look identical. But hopefully, if there are structures, as we can see in this particular case, then we can improve on that. So the second method has to do with the cumulative effect of the other subhalos. So here at about 10 to the 7 solar masses, our sensitivity does drop down, which means that if there's a single dark matter subhalo of that mass sitting on one of the images, we can't detect it, or the effect is too small to be detected significantly. But if CDM is correct, and if there are many of these subhalos, we expect to have many of these tinier subhalos all over our images. So the question now is, cumulatively, all of them together, do they have an effect, a perturbative effect that we could detect that could give them away, and we could measure the cumulative mass of these lower mass subhalos? So the idea there is kind of like looking at image correlation. So if you look at frosted glass, something like that, or something like that, you look at frosted glass and you realize that the images are highly correlated on some length. So in this case, for example, the correlation length appears to be a lot smaller. In this case, the correlation length is bigger. And intuitively, you know that because of the size of the correlation length or the form of the correlation, you can relate it to the structure of the glass. So in this case, you're looking at glass with very high frequency texture, fine texture. And in this case, the fluctuations are on larger scales. So we can relate even intuitively the form of the correlation to basically the power spectrum of that fluctuation that's doing the lensing. So we can do the same thing with lensing by looking at the correlations on top of these perturbations. So the form of the correlations, we can measure something about the power spectrum of the density field, underlying density field. Now, this is, when I say power spectrum, there's one assumption there, and that is that this is a Gaussian density field. So the hypothesis there is that if CDM is correct and we have tens of thousands of these tiny subhalos and are all sitting there, because there's so many of them, they almost form a Gaussian density field to some degree. And so with that, we can just look at the form of the correlation of these perturbations and relate it to the power spectrum of the density field. So we've done that, from a simulations perspective, and shown that it could actually work. Practically, it's going to be a difficult thing to do because these are very, very tiny fluctuations, and so we need to make sure that there are no systematics of mistaking some other thing in the data for that. But generally, what's important to mention is that we're looking at a very particular, so it's not just looking at the size of these correlations, like I said, we're looking at a very particular form of correlation that is predicted by lensing, and we fit for that particular form of correlation. For example, general random noise wouldn't give us that same correlation because it has a different kind, it's uncorrelated or it has a different form of correlation. So if we can measure that power spectrum, now the question is how could we actually relate that power spectrum to the properties of the subhalos? And so if you haven't thought about power spectrum for a while, if you have point sources or point masses in this case, let's say dark matter was primordial black holes, then the power spectrum would be a flat line across all the different scales. And so the amplitude of that power spectrum is just telling us something about the cumulative mass of all the subhalos. So this is an integral over the masses squared. But if the subhalos are a little bit fluffy, they have some finite density profiles like that, then the power spectrum is basically cut. And so it basically has a cutoff, and at higher Ks, it'll be damped, and at lower Ks, it will still look the same. So if we could somehow measure a shape of, for the power spectrum of the density field, we are also probing something cumulative about the density profiles of the subhalos, or how smooth the density field is. So these are the expected power spectra for subhalos in VLACTO2 simulation. So we just took the subhalo catalog out of that and allowed them to have different profiles and different properties, and then we have a cutoff. So the idea here is that anything that is higher than 5 times 10 to the 7 or 1 times 10 to the 7, these are subhalos that will be able to detect them individually, because one of them will have a very nonlinear individual effect that we can actually detect, account for that, and then look at the cumulative effect of anything that's below that. That's why there's a cutoff at, we're looking at things that are below that mass regime. And so these are some predictions for what we can actually measure in terms of sensitivity with ALMA data. So the black is showing what a 10-hour-long integration would do. So with that, we can, in a single source, so this is a single system looking at it, we can measure basically a normalization. If we bin it into 2 bins, we can measure a normalization for the power spectrum. So basically giving us some handle on the cumulative abundance of these lower mass subhalos. But we wouldn't be able to really measure the shape, because the signal drops quite a lot here. So we need to go to much longer integrations, the red curves here, the red error bars, to be able to measure that shape if we want to do that. OK, so I think I'm going to stop there and answer questions if there are any. So these are just for a reminder that 3 different methods that we hope to have in the near future to measure the mass function at the lower masses. Thank you.
So comment and then a question. Comment, so all of this was you posed in terms of constraining substructure within the host. But in principle, there was no reason you couldn't also pick up halos along in front along.
Absolutely.
So just comment that it seems like any comparison with theoretical predictions would need to also include, what contributions you get from line of sight, essentially contamination, although that doesn't mean it's uninteresting, right? In fact, I think that's an interesting question to think about is, for different redshifts of source versus lens, like, are you more or less sensitive to substructure versus isolated structure, and therefore it's in some sense probing somewhat differential regimes of, substructure versus isolated structure.
Yeah, I agree with that 100%. And in fact, the way that you formulated it is exactly what I think about it. That because sometimes people say, oh, this subhalo that you detected, could be at a different redshift, which is possible. But that really, in terms of the data analysis, I don't think that matters that much. But when it comes to the comparison, that's where the key is. Absolutely.
Actually, if I can follow up on that, there's an interesting constraint here, right? Because the halo mass function is supposed to go down to -2. So it's diverging. So the numbers of things that you would expect just from that standpoint that are interloping presumably is somewhat high, but you can rule out to some extent like how far down that mass function must go before you would have too many of those things.
But they're all going to be very low mass. You're only sensitive to
6, to the 5, what I mean, there's,
No, I mean,
depends how far away.
Well, now we're 10 to the, a few times 10 to the 7. So let's say in a very idealistic, universe,
Yeah.
factor of 10 lower.
So for the case you showed, you infer the subhalo mass is about 10 to 9 or something?
Yeah.
So do you expect that there is a galaxy if you take a very deep
So we kind of had a back of the envelope calculation, and it's like, if you, so I don't know exactly, I mean, we don't, but I remember I took a distribution from Yao, and, so that was a halo mass, stellar mass distribution that he had from abundance matching, and just placed it at that redshift. And there's a tiny tail of it that, because there's a scatter, so there's a tiny tail of it that would be above some HST threshold if you sit at it for a couple hours or something like that. But yeah, so we've discussed that, but it seems that it would be very difficult.
Cool. Yeah. So one question is about this probing the very low mass things with in your last slide. So do all the 40 hours that you mentioned in your last slide have to be on the same object?
Yeah, so that's a great question. It's actually funny because there are two sources of uncertainty in there. One is just statistical, and the other one is sample variance. And especially when it comes to longer, so these are the modes. So at the smaller modes, the longer wave modes, a lot of the uncertainty is actually sample variance dominated. So for those modes, actually, it's better if you can look at more systems, and somehow, if you do things carefully and combining them. At higher modes, the sample variance is low because you have more of them, so it's mainly noise. So I think there's a combined strategy between how many that have more of them to reduce the sample variance, or sit longer on a single one to get lower noise. So.
Just thinking if you have like 50 hours of ALMA, you could do 100.
Yeah, I wouldn't sit on one source. Right now, in this cycle, I would not sit on a single
And all the
source.
massive ones you would get unambiguously,
Yeah.
and this would be great data.
Yeah.
And stacking all the
Yeah.
systems.
I think the 40-hour thing is definitely something for the very long term, because first we need to advance to lower masses, do the spectral lines, and then I think we will be in a regime where measuring this the flat part would be possible, or at least we can place interesting limits on it. And once we are there, probably that's the first thing. And then in the long term, if we can actually show that we can do that, and we have a system that we've studied it, all these different things, and we can just say, oh, we can measure that one thing. Maybe at that point it'll be worth it. But definitely in cycle 4, 40 hours on that wouldn't be reasonable. Nick.
Most of the results so far are from SDP-81. So how many other systems like that are there? And do you really need this 25 milliards?
So I showed one of our lenses from cycle 2. So the thing is, we had asked for, so we had wanted to look at 5 sources in cycle 2. And at the time, they offered 1.5 kilometer baselines. That was the maximum baseline they allowed. So and that was the best we could do. So we tried it. And so at that time, we also focused more on this spectral line, because with lower spatial resolution, that spectral line could help you more, because it's breaking the source that you cannot resolve well. So we just received that data a few months ago. And I don't think that any higher resolution data like the SDP-81 has been taken in with ALMA. So that's the only case that we have. In terms of sensitivity, it actually turns out that it's somewhere between these two extremes. And it's a little bit complicated because it does depend on the source of the background objects, right? So if the size of the background source. So if the background source happens to be very smooth and diffuse, then by going to long baselines, the signal has dropped already, so we're just like picking up noise. But if it is very compact, then it's worth it. So with something like SDP-81, I think actually the 16 kilometer was a little bit of an overkill. So somewhere around half of that is, or something like 5-6 kilometer baselines are where it's most suitable for us, assuming that the source size is the same in other systems.
So folks play the same sort of game optically, HST looking at.
Yeah.
So can you just talk a little bit about relative merits of optical versus using ALMA? And is there any systems for which you could combine them that would be useful, or is the source selection simply different that they're basically orthogonal selection?
Thank you very much for asking that, because usually I do have a slide to mention that, but somehow the narrative of the talk has changed and that has stayed. So there are a little bit of background to that is that the first time that this was done actually was with quasar. So with radio quasar, that's the Dall'Ankochanik sample. So there was like a sample of 6 lens quasars. They're in radio, the background quasar, and so you look at the flux anomalies of that. So those are very sensitive because the quasar image itself is very compact, for the same reason that I mentioned about the size of the background source. So because the quasar image is very compact, it's sensitive to 10 to the 6 solar masses and whatever. But you also have fewer constraints. You only have 4 images, 4 fluxes. So you cannot really say this is a 10 to the 6 solar mass subhalo or 10 to the 8 solar mass subhalo. You can just do do a Monte Carlo and just say statistically it seems to be consistent with a mass function with this normalization. And that's what Dall'Ankochanik did. So Simona Vigetti and her group for the past few years, they tried to use the optical lenses so these are the SLAX lenses that typically look like the same thing. So I think they've done great work in terms of developing the system for that. But where I think ALMA is stronger or more beneficial to do is that one is that the signal to noise is incredibly higher. So I showed you this image. We're looking at 160, 140 sigma this is like half an hour integration. The resolution is incredibly higher. So you can go factor of, they do this with Keck AO and they get like 70, 80 milliarcsecond resolution. And the PSF modeling is extremely complicated. With ALMA, we can do high resolution. Another advantage is that you don't have this contamination from the foreground. And so when we look at it in ALMA, with ALMA, that's all we see. We don't have any lensing galaxy contaminating. We don't need to subtract it to introduce any systematics. And there's no added photon noise coming from the foreground lensing galaxy. That's another advantage. And I think the other thing about it is also the same thing about the structure of the background source. So a lot of the systems in SLAX, if you look at them, even with HST images, they look like that. So they look like this image of ALMA. But if you look at the other image of STP81 at high resolution, well, this one is probably a little bit like there's some artifacts in it. But there's quite a lot of compact structures in the background source, clumpy structure in the background source that could be beneficial for us. So I think that we'll see that the sensitivity of these, and there's a large sample too. That's another key. So it can help our statistics. So these are kind of like the general reasons why I thought it was kind of worth investigating this area for the past few years. But so there is this kind of the same thing that I said about the size of the background source, that in the optical lenses, I think the background sources are relatively smooth and big, that the sensitivity to lower mass subhalos is very little.
So is there any downside to ALMA other than, say, difficulty in getting time and difficulty in analysis?
In terms of lens, that's what I think. I'm biased, but I wish it was easier, but I haven't heard of any fundamental objection to this compared to, say, optical lenses. Yeah.
I have another added benefit for ALMA, which is a lot of the star formation in CO2 is obscured. And if it's obscured, you're dealing with dust, which is going to obscure your optical image because your optical image are just in the ultraviolet. And ALMA does not have that problem because ALMA is getting the dust.
Yeah.
So you actually have the opposite, which is you have a reverse K correction.
Yeah.
Goes up,
Yeah. And another added point to that is that when it comes to optical lenses, sometimes the dust reddening in the lensing galaxy is also an issue. So sometimes you see some flux. Like let's say if I saw that this area is dimmer in the optical images, sometimes it's maybe there is like a cloud of dust in the lensing galaxy that's obscuring, whereas in millimeter you don't have that issue too. So you don't get reddening, like differential reddening in the images either. I think so, yeah.
Very curious, how many SPT lenses are as bright as that object?
Actually, this object, this is an Herschel's object. So this is actually not one of the brightest. I mean, it's very bright. I think it's 50 millijansky. Nick, do you know that? Or, but SPT has sources that are brighter. How many? I don't know.
Remember how many are in Joaquin's paper? Tens of hundreds?
Well, in Joaquin's paper, there are like something like, well, we looked at 48 sources in imaging. And out of the 48 sample that we looked at, something about 35 of them are clearly strong lens. There's like something about a few of them that are interlopers from here and there. But in terms of brightness, I think everything that we're looking at there are above 10 millijansky. So, yeah.
Any more questions? But thank you, Yashar, again.
Thank you.
And if you want to join us for dinner, we're going to leave just a little bit early. We'll be show about 5:30.